So on page 41, we're looking at a geometric distribution, which is a kind of a twist on the binomial distribution. All right, I gave a few examples there of what a typical geometric distribution might refer to. So flip a coin until you get heads, roll a die until you get a 6, throw darts to the dartboard until you hit the bullseye. Right? So those are examples of instances where you keep failing until you succeed. Right? So each trial initially is a failure until eventually you reach your first success, in which case the experiment is over. Right? So the conditions are very similar to the binomial distribution. Two possible outcomes. Probability of success doesn't change from trial to trial. Independent events, but the only difference is we don't actually have a fixed number of trials. We just keep going until we get a success. All right. So the example here, how many rolls of a die should it take before we reasonably can expect to turn up a 6? All right. So the random integer function can be found in the toolbox. Let me just get rid of this stuff here. So toolbox, I'm going to just take you right back to the beginning. All right. If you reset a calculator and went in for the very first time, this is where you would land. Probability, go to random, and then you'll see random int. All right, rand int, random integer in the interval of a to b. All right, so we're going to select that. I'm going to put in a 1 and a 6. Now this experiment has me rolling it until the number 6 appears. All right, of course, right on the first try. First try. All right, so it took me only one attempt. But it might have taken more than that. So let me do it again as if it never happened. So toolbox, put in the 1, 6. Wouldn't you know? Right. Let me try it again. I'm just probably the luckiest person alive. Oh, there we go. So I did not get a 6. So pretend this is my first attempt. I didn't get a 6. All right, so that was a failure. Another failure, another failure. It took 4 attempts before I got to the number 6. All right, so it can vary from person to person based off the randomization of it. If you actually rolled a die, you'd see that it's not quite as easy to just land on the number that you want. I mean, there's some people that are skilled at that, but we'll just make the assumption that that's not us, right? So what we do is for any value that's not a 6, we assign a probability of 5 over 6. For the first 6, we assign a probability of 1 over 6. So for example, in this case here, I had 1, 2, 3 trials before I got to the desired outcome. So 5 out of 6 is the probability I would get something other than a 6. That happened 3 times. I would then multiply that by 1 over 6. So my probability, if I want a decimal value or fraction value, really doesn't matter what you're going for. It's a little easier to relate to the decimals. We tend to want to write them as fractions, but it's never a bad idea to have a look at what the equivalent decimal is. All right? So NumWorks will give you both, which is nice. So this is about 0.0965. All right, so around 10% or 0.1 probability. All right, so that would be the instance of getting my first success on the 4th trial. All right, so I got 5, 4, 4, 6. Now the example that I gave here, this pre-printed one from previous experiment, same idea. So let's say my outcomes were 4, 2, 2, 1, 4, 6. My first success is my 2, 3, 4, my 6th trial. All right, so I failed 5 times. There's an implied power of 1 here. That would be my first success. So if I followed that example, I'd have 5 over 6 raised to the 5th power. And so I would end up with about 0.06697, so about 0.0670, all right? So that is the probability that my first success would be on my 6th trial. All right. Now there is a built-in function, right? Aside from doing all these computations and you see formulas and graphs and everything, there is a function in NumWorks that'll compute it for you. So again, it's the toolbox, probability, distributions, then you select geometric. All right, so toolbox, I'll go back. So probability, distributions, you'll see if you go down, you see geometric. And the one we're looking at is the very first one, Geom PDF. It calls for an M value and a P value. That M would be number of trials to get first success. All right, so number of trials to get first success. So I would select, just going back to the last example, 6. Probability of success is 1 over 6. And the result rounds to what we have here, so the 0.0670. All right? So that's actually just one particular outcome from this table that they want us to create. So if I'll read the blurb there. If we proceed in the manner above, we'll come up with the following probability distribution. If I were to assume success on the very first trial, I have a 1 in 6 chance of that happening. All right, I can put the decimal form there, but this is a nice clean number. All right. On the second trial, that means that I failed the first time and I succeeded on the second trial. So for this, easy enough to just type it in. Oops. So about 0.139. Then for success on the third trial, I failed twice. Then I succeeded. So I could take this and just tuck in another 5 over 6. Oops, maybe not. Throw the multiplication symbol there, 5, 6. So about 0.116. Then for success on the fourth trial, you see now making the use of powers is more beneficial. So power of 3 times 1 over 6. So 5 over 6, close it up, raise it to a power of 3. Should do it all in one shot. Then multiply by 1 over 6. And I get about 0.0965. We already figured out 5. So that would be, again, 5 over 6 to the 4th. Did we figure out 5? No, 6th trial. All right. So this one will still do. So same thing, just replacing the power of 3 with the power of 4. You get about 0.0804. But then when looking at it from the perspective of n, rather than raising it to the 6th, 7th, 8th, all the way up to the 1 bazillionth power, we can do 5 over 6 n to the n minus first power multiplied by 1 over 6. All right. And if we were to graph that, we would get a histogram that looks along these lines, showing that it is a skewed distribution. Right? Now, I can put these numbers in to a table. We're going from 1, we'll just go from 1 to 5 to keep it kind of clean. So let me just delete this one and get everything else out. All right, I'm going to overwrite these values here, but I'm going to do it using the geometric PDF function. So I'm going to go to OK, fill with a formula, wipe this out, go to my toolbox, select geometric PDF, put in the M value, number of trials, to get the first success, which is what I have in my V1 column. So Shift Alpha division to bring up V1. And then the probability of success, which is 1 over 6. And then hit OK, and it'll populate all these values into the table. All right? And if you look at what we wrote and compare it to what's in the table here, you see that they're pretty much the same. And if I create the graph out of this, up, over, histogram, it's along the same lines. This one goes out a little further, but you see it still has the same structure. Now, if I go into stats and I pick out the population mean, mu, right, so mu is equal to 2.641, and my standard deviation, 1.384. That's not quite what the formula says the mean of the distribution should be, but that's only because it's a small number of trials. Right? If I had a bunch more trials, it would start to settle in on the actual mean. So let me just show you real quick. This is more enrichment, not anything I would put on an assessment, but let's say I wanted to go out to 100 values. So value V1, fill with a formula. I want to go out to 100. All right. And then do the same thing with the geometric PDF formula. All right. Everything in V1, it held on to what I had before, which is really nice. I think that's part of the new upgrade. V1, 16, hit OK. It'll fill my list. And then when I go to stats, you see my mean is practically 6. All right. And so if you think about it, the probability here was 1 over 6 in this scenario. Mu would then be 1 over 1 over 6, which is equal to 6. The variance is a little bit more challenging to come up with, so I won't bore you with that, but it does work. All right, the technique does work. I mean, I'll bore you in the sense that I'll actually do it, but I won't, make you do it, I guess. Variance, abbreviate that with S squared if you want. I'm sorry, sigma squared, because it's population. So 1 minus 1 over 6 over 1 over 6 raised to the second power. That should give me something in the neighborhood of 5.477. All right, so let's see. Oops, not 16, 1 over 6. And then 1 over 6, close it up, raise it to the second power, and you get 30. And I apologize, I believe I said you should get something in the neighborhood of 5 point whatever. I was looking at the wrong number. That was the standard deviation. I want the variance. All right, so standard deviation would be the 5.477. The variance is very close to 30. Right? So yeah, you could use formulas to get it. You can come up with a table with large number of values to get it. Either way, but you're going to get it. Right? So the example here, during one game, an NBA player takes 7 free throws. Throughout his career, he's been a 75% free throw shooter. So we can assume in general that his probability of success on any one trial would be 0.75. We also assume that each free throw is independent, although maybe it's not. I mean, sometimes you get the yips, or you just have a bad day, your elbow's hurt or something like that. Making a foul shot will be our definition of success, and missing it will be failure. We want to know what the probability is that he will make his first free throw on his last attempt. So that's geometric, PDF. He's going to get it on the 7th, and he's got a 0.75 chance of making it. So in my calculation app, Geom PDF, 7.75, lock it in. very remote possibility. So 1.83 times 10 to the negative fourth. The mean of the geometric distribution would be 1 over whatever the probability is. So they said 0.75. So 1 over 0.75. You could say 1 over 3/4 if you want. You get that value. You could say 1.3 repeated, or you could say 4/3. Keep it clean. Right? That's the number of shots it should take before he makes the first shot. Standard deviation. So variance is 1 over, that's this formula, 1 minus p over p squared. So we're going to do 1 minus 0.75 divided by 0.75 squared. All right. So 0.4 repeated, but that's, again, that's the variance. The standard deviation sigma is going to be the square root of that number. So square root of that answer, and you get 0.6 repeated, or you could just say 2/3. All right, some nice clean numbers here. And then complete the table. Now, we're not using one of our stats because we're using the numworks. But it's essentially what we just did. So you go into stats. We need 1 through 7. So I'm going to wipe out this column here. I'm going to type in, well, wipe out the whole thing. 1, 2, 3, 4, 5, 6, 7. Then I'm going to put in my rule under frequency, fill with a formula, empty, geom PDF, lock it in. My information for the number of trials to get a first success is in V1, so I do shift alpha division 1, and then the probability of success on any one attempt is 0.75. They told us that in the open. So these are our probabilities, and I'll get my mean and standard deviation from, I'll put all this stuff in the table, but to get my mean and standard deviation, I'm going to go to stats, about 1.333, which is about what we got here. And then for the standard deviation, about 0.664, which is in the neighborhood of what we got there. Small number of trials, so that should make sense. All right, it's not going to be precise, but it should be in the neighborhood. All right, let me just get these values in. Just round to 3. Significant 0.0117. 00293. And then 7.32 times 10 to the negative 4. 1.831 times 10 to the negative fourth.